Is it okay now? Is it okay now? I talk. Good morning, everybody. This is talk about C++. C++ is now 1 year old, and what means we have 1 year more experience about it. And turned out that in practice, a couple of things are interesting. And both, it's fundamentally great to use these new features, and it's fundamentally sometimes, well, let's say, surprising. And I've selected this hour to talk about both, the good and the ugly. There's not many ugly, so this was just to get you all into the room, because you all like bad news, I know that. So, but there is some things you have to be aware about, and that's something I want to show you. So now it works. Let's start with the language features, and this is just a selection of the different features we have. So let's start with the first thing we have. This is a new ability to say, whenever we define something in a header file, which is globally or static, it's no longer necessary to define this object in a CPP file, so that it is in one translation unit defined. Which effectively means that you can now provide full libraries, including providing global objects just in header files. Here's an example for that. One of my typical things I always need and try out is just the tracker of calls of new and delete, so to find out when is memory allocated and when not. And in the past, either I could put everything in a header file, or I needed some tricks like static functions, or I had to be sure that this header file is only used in one of the translation units, but this is gone. Now you can simply say, this is my class, including some static objects, so where we count the number of calls of malloc and the size we allocated, and just by including this header file, even if you include it in 10 different compilation units, so in 10 different CPP files, you can now track all the calls of new and delete. Because the new feature here, inline static, means that we have these elements defined for each and every translation unit, and they all share the same object. So it's inline now for global objects. That's the first thing, just to wake up. Now let's come to something different. Templates are a beast, and templates are always, well, some kind of interesting surprises. So let's introduce one of the new templates features, and we will come back to it later today. And the first thing I want to introduce is a feature called Class Template Argument Deduction. The acronym is CTAD. Please note it. We will talk in the community a lot about this acronym. And that means that in our classes, you are no longer required to specify the arguments of a class template if the arguments can be deduced by the constructor. So look at this. Normally, we are all used if we want to have a complex data type that we have to specify. This is a complex of int, although we specify that both the initial value for the real part and the imaginary part is an int. This is no longer necessary in C++ 17. We can now just let the type of the values of the real part and the imaginary part deduce according to the constructor, independent which notation you use for the constructor, whether you use curly braces or parentheses or even the equal sign because you initialize only the real part. The type int will be deduced here because you pass to the constructor an int. This works as for function templates. So also for function templates, types are deduced according to the function. Now for classes, the types are deduced, if possible, for the classes according to the constructor called. The constructor for complex takes the same type T for both the real and imaginary part. Therefore, the next line is an error. Because the compiler has no clue what to deduce here, we say the real part should be an int, the imaginary part should be a float, or a double, so there's a contradiction, and this will not compile. This example can be used in other places. Here's an interesting place. It's a mutex and a lockguard that uses this mutex. In the past, we always had to specify the type of the mutex, which was a little bit nasty, so you had to write lockguard of std mutex, and if you used an std recursive timed mutex, that was a lot of characters to type. Now, simply the constructor makes it for you, because the constructor takes the mutex, then the type parameter of the lockguard template is used. And of course, this also works for containers. So now we can use vectors, and we don't have to specify the element type if it's clear what the element type is according to its initialization, so according to the constructor we call. So here are some examples. Let's declare vector initialized with the elements 8 and 15. As you see, I don't say that the element type is int. It will be deduced because we have a couple of constructors. So what happens here is the compiler tries to find the constructor that should be called here. Well, we have here all the constructors listed, and the last one is it. According to the overloading rules, the last one is the one called. We have by priority taking the one with the initializer list. And in the initializer list, we say it's an initializer list of T. And because we have T there specified, we can deduce that because the elements 8 and 15 are ints, that the type T is an int, which of course would not work if we would have different data types there, for example. So that's OK, that compiles. And that also compiles for only one element, like here. Well, I told you we have to talk also about the ugly pieces of C++17, or the little bit strange or nasty consequences of that. So there's another interesting consequence. If you now specify the initialization with parentheses, you get a problem which we also introduced in C++11, because we have, unfortunately, some history, and the history says that there's a constructor that takes a size and then an initial value. If you don't use curly braces, the last constructor is not used. Initializer lists only work with curly braces. So another constructor will be used. The constructor that will be used will be the fourth one, taking a size and a T, or a const T reference. And that const T reference is an int. It's the int 15. So what we create here is a vector of int with 8 elements, all having the value 15. This is probably not intuitive. We now have brace initialization. Please use it. It's better than anything else, even if others claim that this is wrong. They have no clue because they don't like change or to learn. We can't just specify the 8 with parentheses, because the only constructor, or the constructor that would fit here, would be the third one. And the third one doesn't deduce T at all. It's just a number. So therefore, this will not compile. And by the way, I should say something here. If you pass 8 and then a string literal, that will also not work. Why? Because we take in the force constructor, we take the parameter T by reference. And if we take parameter by reference, that means that the string literal is not decayed, which means we take the original type of the string literal. So if our string literal is high, or hei in Norway, H-E-I, you have the type an array of 4 constant characters, and you try to instantiate this template by being T an array of 4 constant characters, and that's not allowed. So that will not compile. And here's another thing that will not compile, which is, let's initialize this by elements of another container. So we have a set of strings, and we do something in between, and later on we decide that we want to initialize a vector by all the elements that are currently in S. This will not compile because we don't find any appropriate constructor where we can easily deduce type T. There's a constructor. The constructor that's obviously taken is the one in the middle, taking 2 iterators and an optional allocator. And but this is not used because how do you deduce type T from here? So how do you deduce the element type that the vector should get? Well, we decided it's important enough to introduce another feature for that, and the feature is deduction guides. So we can help the compiler to deduce the type of the template according to the way we construct the objects. And that's a deduction guide, and you see it here. This deduction guide, look at the syntax, looks like a declaration of a constructor. It's outside the class, but in the same scope where the class is defined. That's important, both is mandatory. And with an error we say, well, if I initialize a vector with 2 arbitrary iterators, well, let's deduce that the vector element type is the value type where the iterators point to. Peter?
I have a question. The second last line, wouldn't that use the vector of 2 set iterators? Using the initializer as constructor, use type as the set.
So the question is, the last but second line, wouldn't that now call the initializer list constructor? As far as I know, not. I'm not sure I immediately have the answer for that. We're talking about the nasty darkness of overloading roots and when things match. Probably the constructor taking 2 iterators is a better match because it has no type conversion. Maybe not. But I'm pretty sure I'll try that out. But I might be wrong. Never trust anybody teaching anything about C++. Nobody in this world has understanding of all the features in C++. Yeah, I have to check it afterwards, but I thought I tried it out. Okay, we love C++. Here's a complete definition because I skipped in the deduction guides, I skipped the allocators. And so that's a complete way to say, let's deduce the type of the elements from the iterators we take to initialize the vector. So now there comes another interesting thing. What happens if I pass 2 string literals? Think a little bit about it. Which constructor is called? We have curly braces, so it could be an initializer list. But this is also 2 objects, so any other constructor taking 2 parameters might be called. So we have a couple of other candidates. And yes, you know what? The initializer list constructor is taken. Whew. So we have here the right thing. We have initialized the constructor taking 2 strings. We pass an initializer list, and this is initialized by a vector of const char t, because t and the initializer list is not a reference. The array type of the elements is deduced to become const character t. So let's use parentheses instead of curly braces, which rules out the initializer list constructor, because it always needs curly braces. Which one is called? The nasty answer is the one taking 2 iterators. Because these are 2 string literals which decay to const character star. Const character star means we have 2 pointers, and pointer is a valid iterator, and it is used. The funny thing is that the first iterator is the address of high, and the second iterator, which is the end of the range, is the address of world. Which means that the elements inside are characters, const characters. That is deduced, but if we are lucky, we get a cordump, because when high is in a location in your program after world, so we get no real distance between the two. Funnily, you get at runtime an allocation error, because your program probably can't allocate all the amount of memory that lies between these 2 string literals in your program. If it's the other way around, so high is just in front of world, it might work. If there's something in between, it might have suddenly, I don't know, 100 elements. So this is undefined behavior. This is a very nasty runtime error, and maybe we should fix that. It's not easy to fix that, because we want to initialize a vector from containers where, for example, by another vector that has characters inside, and the other vector natively might use iterators that are ordinary pointers. So we have no easy workaround. This is another problem which we got from C, where we have no difference between arrays and pointers, etc. This is ugly. But you have seen it already. So always initialize with 3 elements. That's the rule you learn from that. And by the way, it's always better to use curly braces than parentheses. That's the other rule, and I'm serious about that, because people still think parentheses are better than curly braces. We don't have this problem with curly braces. Okay? Let's go to the next feature, compile time if. Compile time if means that at compile time we can decide which part of a template or even of a non-template is used and compiled. Here you see an example, and this is a good example because it will not work with runtime if. Look at this. We try to convert any type we pass and value of any type we pass to a string. And we try different approaches. If it's an arithmetic type, so integer or floating point value, we call to string. Otherwise, if it's a string, we just return the string, and otherwise we try to call a constructor. The important thing here is if we pass 42, 42 is an arithmetic type, so toString is the appropriate thing, but the third, the else statement, would not compile for this type. So if we have a runtime if means all statements have to be valid. With a runtime if, this code would never compile. None of these applications. So with a compile time if, this will compile because the return constructor, the last return statement, is discarded, as we say. And that means that it will be ignored provided it depends on a template parameter. If not, it will try to be compiled. Then it has to be valid unless you use Visual C++. Because they don't implement templates rules correctly for years now. They know that. They have to fix that. Unfortunately, the fix will break existing code. So there's an interesting new option for the compiler now, /permissive-, where you can turn on turn on correct handling of templates, including correct handling of const exp if, and then see whether you made everything correct. One common error is that I assume in the first case, as string of 42, that if in the else part I have an assertion, that this assertion is not triggered. This is wrong. It will be triggered unless the assertion uses type T, or the object X. Because as said, and as for templates in general, discarded statements that are ignored because according to the compile time we know that they are not used, are only really ignored if they don't depend on the template parameter. Otherwise, they are part of the first phase check of templates, and they have to be valid. So beware. Here's another example. We have a new way to initialize objects. Well, to call an if statement. This is a new if. We were so successful with for loop becoming different, and that we thought, oh, it's a good idea to extend our control structures even more. So now we have an if with an initialization. Here you see what you can do. You can say if, then you have an initialization, and then you have a condition. You can do that with if. You can do that even with if constructor. So with the compile time if, then the interesting thing is the initialization might be a runtime issue. The condition is still a compile time issue. So look at this code. This is something you can write now. In my if statement, I initialize a lock guard. That means I try to lock a mutex. This is initialized at the beginning of the if and will be destructed at the end of the else, if there's any otherwise at the end of the if. So in both cases, in the then and in the else part, we have the mutex locked so that we can use use the object that is protected by this mutex, either in the then or in the else part, which is decided at compile time so that no unnecessary code is generated when we know at compile time, for example, what is the value type of the object passed here. Okay? Another caveat here, don't forget to give a name to the lock guard. If you don't use LG here, then you are locking a temporary object which is immediately unlocked before we come to the condition. So the lock no longer works. A couple of people like this and say, well, let's use the underscore here to make clear I don't care for the name, but I need a name, so underscore is good. It's an interesting question whether this is good or bad style. Good. And with this compile time if, we can come to a couple of other things I want to discuss about the call language at the end. Who's familiar with variadic templates? A few. Okay. Variadic templates is from C++ 11. Hey, we have it now. 7 years. Time to learn it. This is an example of variadic templates, and it works roughly the following. You say, my print takes one argument of any type and an arbitrary number of arguments of an arbitrary number of other types. By saying type name ... and then types ... and then later on args ... you say this is representing a so-called parameter pack, so a couple of arguments, either types or objects. How is this used? Well, if I call, for example, print for 3 arguments, then the first argument, first arg of type T is hello, and the other arguments are multiple arguments of different types. So what this means is, when we follow the guidelines of this print, let's print out the first argument and then call print for the remaining arguments called args. And that means we recursively call ourselves. And that means now the first arg is a double. We print the double. And we call print again for the remaining args, which is only one. And then let's call this print for the remaining arg. And call print for this first arg string. And the remaining args is empty. So let's call print for empty. And empty is a special case. We have print for no argument. And effectively, as this is a template, this will be done at compile time. So effectively, the code generated here just prints out all the arguments. Good. This is C++ 11. So can we improve this a little bit? OK, here's the first example. Let's check how many arguments we have. We have size of ... We can say how many remaining arguments are there. And the rough idea might be, well, if the number of remaining arguments is 0, I end the recursion. I don't call print again. Unfortunately, this does not work. Because I just told you, templates instantiate everything. This is, you are using a runtime feature, but the question whether print is called and has to be provided is a compile time question. So even if you have only one parameter passed and the remaining arguments are empty, you have to have a print for an empty list of arguments, otherwise this does not compile. But now we have C++ 17. So what do? We use a compile time if. And with a compile time with, this works. This ends the recursion. Can we improve it even better? Oh yes, because compile time instantiation, recursive compile time instantiation takes a lot of time and resources of the compiler. So let's invent something better. We have something better. For these cases like this is a fold expression. Fold expression is a new feature of C++ 17, where you can say, for all the arbitrary number of arguments I give you here, please combine them with the less than operator, and on the left there should be stdc out. Look at this. The expression is in parentheses, 3 dots in the middle, and then around your parameter pack and your initial value and the operation, which has to provide it twice. It's not allowed to have different operations there. So this will print all the arguments. Unfortunately, the arguments will have no space in between. And you can't say internally in this folder expression, there's another argument so that we print a space before we print the arguments. Hey, but this is C++. So let's do something better. Let's call a helper function, a helper template, that prints out the space before we send the argument to cout. OK? So we print here the first argument because it should not have a space before. But for all the other arguments we say out, we sequentially print them out to cout by after we printed a space before. So space before prints first the space and then the argument. This would have been undefined behavior if we would not have fixed something else in the standard. Because what is essentially called here is the statement on the right, on the bottom of the right. So essentially we compile print to cout space before the second argument and then space before the third argument. Before C++ 17, it was not guaranteed when space before is called. So space before might be called twice. So we print 2 spaces. And then we take the outcome of space before and write them to cout. So the outcome might be 2 spaces, then the 7.5, and then world without a space in between. What I'm talking about here is a fix we have. Here you see another example that was one of the motivating examples. This code was broken before C++ 17. I have a string, I want to replace the first 8 character, and then I want to replace even by sometimes, and you don't by I. And the point was, it could print if sometimes it sometimes work if I believe. This would be the case if really the find statement is evaluated after we replaced the first 8 characters. But it turned out that there were possible other outcomes of this. Or what people also usually think is, in this output statements, f is called before g, which is not guaranteed. So if f depends on the outcome as it has a side effect from g, this did something different. And the other example, let's print out I incremented and then I decremented. The outcome of this, depending on your compiler, could have been all these combinations. So we fixed that because that was too confusing for a couple of people. We define now new evaluation fodder for a couple of other operations. Before we did it only for AND, OR, and the comma operator. Now we have it for more. You see them here listed. Please note that we still have no defined order for the arguments in a function. We only specify that if we have a function, the left part, so the expression that defines which function is called, is evaluated before all the evaluations of the arguments. And therefore, the example you just saw works and is guaranteed to work correct. We can make it up even better. So just to give you some more clue about the fold expression, you can do it that way. Look at this. Look at the statement at the bottom, the red statement at the bottom. This is a fold expression saying, I'm using the comma operator to call a sequence of the lambda for each of my arguments. So this is effectively compiled as follows. It says, after printing the first argument, we print out with space for 7.5, comma, out with space for string. And things like that will now happen. Maybe not in your code, but at least in libraries you use. OK. And there's something else. Let's parameterize this, because is it a good idea to print a space here? No, of course, we should be able to specify what is printed here as a separator between the different elements we want to print. So we have another feature called auto parameters of templates. So I can say now my separator that should be printed between the different arguments is by default a separator being a space. The auto here means I don't require that this is a character. It could be something else. And by doing that, we could say, OK, let's use the default. So let's print a space between all these words. Let's use a single other character. I could pass the int 7. So between all the different words, I would get 7. There will be applications for that, I'm pretty sure. And we have another way, we have another feature now. We can now pretty close define that there's a string. You still can't directly pass a string literal to a template. That will hopefully come with C++20. But you can do it now that way. So you need 2 lines. You first have to declare a static const array, so comma space. And if you pass this to this print function, the auto becomes an array, a pointer of characters, and is used here as a separator. So you print out hi, comma space, 7.5, comma space well. That's another feature we had, the auto in templates. OK? Good. Let's skip that. Let's go to the library. Sorting, well, optionals. We have introduced options now for those who know Boost. It has been there for a long time. We can now say, I have a value that might be there or might be not. So I can say, if I have an int, I have an int. I have no int at all. Or for a string, I have a string or no string at all, which is different from being the string empty. So if you need two different states for strings, distinguish between empty string and no string, this is possible with optional. And optional can even be sorted. Look at this example. You can say, let's initialize a set of optional unsigned values. The first optional unsigned value is 42. The next one is I have no unsigned value. That's null up now. In Boost, it's none. And then I have a couple of other values. Then I have null opt and minus 11, which gets converted to a very big number. And then 777. So, and now in a for loop, let's deal with all the different elements in this set. That means we have a for loop over optional unsigned. So I first check, is there an unsigned? If not, so is this an optional value? If there's no optional value, then print there's no value. Otherwise, if it's greater than 100, see, we can compare directly with the underlying type, so with an unsigned. I print this is the value with star and append a big, and then otherwise I print the value. So I get output like this. Looks nice. It's helpful. As usual, Bjarne said it yesterday at least, that, well, every new feature is overused. So be careful not to use everywhere an optional value. Just only use it if all the other values are not good enough. And you have some surprises. So here's the first surprise. If I have an optional bool and I test whether this optional is less than false, the answer is true. Because the rule is that any value that is not set is less than the lowest value of the underlying type. So the values are true and false. So no Boolean value is less than false. And the same is true for optional unsigned. If I have an optional unsigned, it makes sense to test, do I have a value less than 0? Okay? And you have some other consequences. If I have an optional bool, there's a difference between if no optional and if optional equals false. In the first case, we check, is there a value or not? In the second case, we check, is there a value that has a value false? And the same is true if I have an optional raw pointer. Is there a value is the first check. The other check is the value not null pointer? So we had some discussion whether we want to enable this or not. That's, by the way, the reason optional comes with C++ 17 and not before. We decided no special handling, so you know that now. You have seen my slides. You don't make this error. There's another problem with optional. If you have a function returning an optional string, and then you call a function giving you the value, then beware that this is a reference. It gives you a reference to the underlying value if there is some. If not, it would raise an exception. So the naive application of this, what people started to use is, let's take a function, get vector, that returns a vector of int, and then we iterate over the values. I need the ability to return that I don't have a vector at all, instead of returning an empty vector. So what people do is, they switch to an optional vector of int, and in the loop they say, well, let's iterate over the value of the optional int. The problem is, getObvector will return a temporary object, .value will give you a reference to that, and the moment you have the values and start with the loop, the temporary object is gone. So you access values of an object that's no longer there. This is something we have to deal with, because more and more we're talking about new types that deal with reference semantics, and we discuss solutions for this problem. And by the way, I know one big company that for problems like this is not only a problem with optional, this is in general a problem if in a range-based for loop you create a temporary and you call in the range-based for loop a member function that gives you a reference to this object. And there are companies who say, well, you shouldn't use the range-based for loop because of that. Okay, we have to fix that. Here is another type, variant. Variant is a new union type. You can say I have different possible values. One of the values I have, you can even have so-called different alternatives of the same type. Let's look at the application of this. This is cool. This is one of the coolest features we invented with C++17. Well, we didn't invent it. We adopted it from Boost. And look at this, the consequence. If you have runtime polymorphism, so you have a base class geometric objects and you have derived classes that are different geometric object types. So you have a circle and a line, and they have implemented virtual functions to move and draw the objects. So that you can say, let's create a vector of geometric objects, an inhomogeneous collection. So we need a pointer there. That's a drawback. We need a pointer with runtime polymorphism. And then, because we need a pointer, we have to call new. Otherwise, we insert something that goes out of scope if we insert the address of a local object. And then we have to use pointer semantics to deal with it. And then at the end, don't forget to call the delete. Yeah, new and delete is evil. You shouldn't use that anymore. We have some workarounds like unique pointer, shared pointer. They have their own flaws. Here's some really cool solution for this problem, provided you know that this is a closed list of different geometric objects. So that means you know all the different types. The alternative is use a variant. Use a variant that says, my element type is either a circle or a line. Now, you no longer need pointers. You get back value semantics. That means you don't need new and delete, and you don't run into the problems of using new and delete. So you can now say, let's push back a new line, let's push back a new circle, just by value. I return this, a vector of elements that are either circles or lines. I iterate over them, I print them, and here's the interesting part. Here is the part where we need polymorphism, because now I want to draw these different objects. And normally we would use runtime polymorphism here. Here we use a function called visit. Visit is something like a little local vtable implemented. So it says, I call for my element types the right function object taking either a circle or a line. So you can pass here different function object that has different overloads of the function call operator, or you pass a generic lambda. A generic lambda is a template that is callable for both a line and a circle. So what we program here is we have programmed two lambdas, one taking a circle, one for a line. And if it takes a circle, it calls draw for the circle. Otherwise, for the line, it calls line draw for the line. And the visitor has internally a jump table or something like that to call the right thing depending on the argument type. So this works. And you don't need any delete anymore. You have value semantic in this polymorphic approach. The only restriction is you have a closed set. So the variant has to know which different options you have. And forget about base class, forget about virtual functions. We don't need them anymore because this is not using the usual runtime polymorphism. Just have different values, different data types, and it works. It could be an std string, it could be an int, could also be a variant here, and you could have defined different handling for different types in the visitors. How do you do that to define different handling in visitors? If you prefer to define handling of types in a lambda instead of a function object, because function objects are more complicated and you can't easily program them locally, here's a way you can do that. Look at this. I want to have different implementation how I handle circles and lines in my example. So I call visit, and I overload two lambdas. One lambda dealing with a circle, one lambda dealing with a line. And here you can have totally different code. So how is it work? What is overload? Overload will hopefully standardize in C++20, but not yet. Look at this. This is the definition of overload. It's 4 lines of tricky template code. So you define, look at this. What I define here, overload is taking, is a constructor, is a data type. So we create an object, and we initialize it by 2 lambdas. This is a template. So first of all, we need class template argument deduction to deduce the type of the lambdas. This is a variadic template, and we deduce all the types of all the lambdas. And for that, we need a deduction guide. Look at the end of the definition. We say, if we initialize and overload objects with different functors, please deduce all the functors to be part of the declaration of this type. And then we have, how do we deal now with these functors? So we have a struct overload taking these different functor types and passing them to the base class. So we derive from the data type of the first lambda and from the data type of the second lambda. You got that? And then we say, I want to, in my class, inherit all the different function call operators we have in all the base classes by having a using declaration there. That's it. And that way it works, and that way we have now a feature to overload lambdas so that you can have different behavior. And if you want, you can say the first lambda takes auto, that's a general case, and I have special cases for other types. Okay? And that way, runtime polymorphism is now replaceable as long as we have a closed set of different types. I like that. So, a few other things. I have 10 minutes left. First of all, let's effectively sort strings or substrings. So let's initialize a vector of strings so that the elements are ID0, ID1, etc., but we have both ID with lowercase and ID with capital case. So the elements are there. So I want to sort them 2 ways. I want to sort them in general, and I want to sort them according to ignoring the first 2 elements, so that the first 2 elements should stand behind each other. Because otherwise, if we sort them in general, all the lowercase strings would be in front of all the uppercase strings. Okay, we can call sort. Just the ordinary sort. We have sort for strings that compiles and will sort the elements so that we have the lowercase ID0, ID1, ID2, and then as a second part, the uppercase strings. We can say, I want to ignore the first 2 characters. So by doing that, we might say, let's take the substring. Let's take a substring. So let's ignore the first 2 characters. Unfortunately, this is a pretty expensive operation, because substring creates a new temporary string. So for each element, we create a new string for both elements, and then we compare. This is really expensive. You see the different behavior, the different performance here. So we have a factor of 3 worse in this program. This is no proof that it's always factor 3 worse. It's just on my laptop. Tried it out with a couple of compilations and different number of elements. So what can we do? We have a new type called string view. Instead of using a string, we can create a view to a string, which refers to the underlying data of the string and call substring there. And by that, look at this. We have almost roughly the same performance. I would not claim this is faster than before. This is too close to prove here something, but this is close to that. So what we use here is a string view. A string view is something where you say, I have something that looks like a string, but it does not own the characters. So here's an example. That's my string view taking hi. Well, beware. You might provide a function adding two string views, like here. Of course, the outcome is a new string. So we declare plus for two string views, and then the outcome is a new string we create. And then some cool guy might say, oh, I have a template called concat, which adds two values of type t and returns this type t, which looks pretty reasonable, but it's not that reasonable because you have claimed here that the sum of two objects of type t always create a t or convert to a t, which is a nightmare. Now let's call this for the string view. So what you get is, you get a sum object temporarily created in the operator plus. And now the return value converts, because we return a t, converts to a string view, which means we have an object referring to the characters of this temporary object, and then we leave the function. Bingo. We return an object referring to memory that was freed. And then if we use it, we have a runtime error. So there are some issues with string view. Be careful. It's good if you take it locally and you know it's the object they refer to is still there. It's at least dangerous if you use it as a return type. And by the way, this is a good example to prove that it's a good idea to use auto as return type in generic code instead of a specific type. Because by using auto, you disable implicit conversions in the return statement. Okay, I want you. So, can we still improve this example? Where we said, let's use strings instead of a string view? Yes, we can. Because we now have parallel algorithms. So let's use them. That's easy. Add a first argument in front of all the other arguments. So just add execution par. Please execute this in parallel. Do you think you get a better performance? You never know. It depends on how long it takes to start a thread. On my laptop, with 2 cores and hyperthreading, this is the outcome. So there is a significant factor on my laptop, but that might be different on your system wherever you have it. But you see, there is a chance. And at the end, it turned out that the parallel execution using string views is even faster than the original simple sort. Okay, that's a benefit of parallel algorithms we have. We have other examples for that. I will show them in 1 minute. First of all, I would like to introduce my last topic, file system library. The file system library now is updated, is introduced, adapted to C++17. Yeah, this looks pretty okay. I mean, I can pass here path, and if the path exists and is a regular file, I print this is a file with this size. If it's a directory, I print the elements, etc. So this is code we more or less adapt from Boost, and where we only have to change the header file and the namespaces. So if we come to the case where we iterate over a directory, the outcome might be this on Unix. If I run this program on Windows, the outcome is this. Because we print out the elements quoted. And quoted means every backslash has an additional backslash. Ugh. Yes, we standardized that. I think this was a mistake. But anyway. So what do we have to do? Call string, so convert pass to a string and put double quotes around to make this really portable to different platforms. Okay? So you see, in every little thing we adopted in C++ 17, there is something, some drawback we have to talk about. And that were not all examples. That were those that fit into this hour. So let me close this talk by 2 slides. The first slide is this. Please use brace initialization now. You will detect narrowing. You will not run into problems we saw by initializing a vector of 2 strings. You can initialize a vector with 2 elements. It's self-explanatory. We have fixed in C++ 17 the combination of curly braces and auto unless you use an equal sign. That's a big mistake we made in C++ 17. So don't use the equal sign with braces. We have now introduced enum class initialization with braces, which was not possible before. And that's the only way now you can initialize an enum class object. We have extended aggregate initialization so that you can use it. And so please use it. Please use it. There are still some flaws we have to fix. For example, in atomic. For example, somewhere else that will be fixed in 20. But now, brace initialization without the equal sign is far better than anything else. It doesn't serve all the purposes, but it's far better. So that's it. Jakob is looking already. Is this clock correct?
Just 45 minutes to go.
I only have 45 minutes? I thought I have 1 hour.
It's a great talk.
Oh, good. So, sorry. Excuse me, I really didn't know that. Yeah, normally I don't over. So, replace by the next talk. Sorry for that.
Go straight to the next talk.
Yep. Yeah, sorry for that.